26 deals with interference and diffraction. Interference and diffraction are usually lumped together in a branch of optics called physical optics. It's different than what we did in the previous chapters where we were treating light like a ray. We treat it like a ray, we call that ray optics or geometric optics. When we treat it like a wave and we start looking at interference and diffraction, we call that physical optics. In order to have this discussion, we need to understand a little bit of terminology. I want us to start with looking at the idea of monochromatic light. If you know your Greek and Latin word parts, you realize that means one color. Most light that we have access to is not monochromatic. Most light is white light. But even when it sometimes looks like it's red light or blue light, it actually might contain other colors mixed in to create that. Our best source of trying to get light that's single color, which is really an ideal. Single color means you have exactly one frequency of light. And like a number line, you know, what's the difference between a frequency of 5 times 10 to the 14 hertz and 5.1 and 5.01 and 5.001? You could keep making that smaller. But our best source are lasers. They are almost monochromatic. A typical helium neon laser, this is a red laser that you've probably seen before, helium neon. It would probably have a wavelength that was 632.8 nanometers, plus or minus. That's 1, 2, 3, 4, 5 zeros, and a 1 nanometer. This is called the bandwidth. This is how wide a range of frequencies we have. And as you can see, to a tenth of a nanometer at least, this is a single color of light. Okay. Another idea we need to understand, we've already studied when we talked about waves, and that's the principle of superposition. And that basically says that when two waves, and it doesn't have to be two, it can be two or more waves, occupy the same space, the resulting wave is the algebraic sum of the individual waves. And we looked at that principle back when we were studying mechanical waves like water waves or sound waves. Okay. If I have two waves that are in phase, you can almost think of that as being in step. Their peaks occur at the same time and their low points occur at the same time. If I draw it, let's just draw your basic, okay. If I have this wave and I have another wave that has, I'm trying to draw these where the peaks are at the same time and the lows are at the same time. If this one has an amplitude of A, and this one also has an amplitude of A, I didn't draw that very well, but you get the idea. if I were to add those two waves together, I'd get a new wave. And my new wave now has an amplitude of 2A. Anytime you have waves which result in getting a larger amplitude, this is what we call constructive interference. If we have two waves that are out of phase, and in particular if they're out of phase by 1/2 cycle, that means when the first wave is enjoying a crest, that the second wave isn't having a trough. Notice here we have a crest, here we have a trough, here we have a trough, here we have a crest. If I were to add those two waves together, they would actually result in a 0 amplitude wave. Okay? That's a case of complete destructive interference. Now, you can have destructive interference without it being completely destructive. I could have had a smaller wave here. Where maybe this one had an amplitude of 2A and this one had an amplitude of 1A, and they would still, when I got that, what would happen is I'd get a wave that resulted in a smaller amplitude, but not completely wiped out, okay? But this wave would be taking away part of that. Okay. So I think you should already understand what we were talking about when we talk about constructive and destructive interference, and what we're talking about when we talk about that principle of superposition. So let's assume that I have some source of monochromatic light, like a laser. Could make this a color. So here's my laser. Obviously, a laser beam's not usually nearly that big, but that's okay. We're going to draw things that are definitely not to scale. And I put a screen in front of it. But I cut two small slits in that screen. Tell you what, I'll make those slits a little farther apart, just to make it easier to draw. There it is. There's a slit. There's a slit. Okay. Really important. This is monochromatic light. Okay, from a single source. If we think about it, if I pick some point over here, if I go directly straight across to the midpoint, right here, that point has to have constructive interference. And the reason being, oops, you need a ruler, I think, to be kind of straight. The reason I have to get constructive interference here is because those two light rays that are coming through those slits are what we call coherent light. They're the same color, and it's going to be in phase with itself. Well, in this case, if they're both are going the exact same distance, and that's my assumption there. If I call this R1, and I call this R2, if R2 equals R1, that distance is the same. We are going to arrive in phase, and we're going to get constructive interference. Let's change that up, and let's think about what happens if I go to a different point. What if I told you there is another point where I also got constructive interference? Well, obviously this time they're not going the same distance. In fact, the way that I've drawn it, let me be consistent with my notes, okay. This one's R1, this one's R2, and clearly the R2 in this case is longer than R1. But if they arrive in phase, right there, so that we get constructive interference, well, the only way that can happen is if R2 is longer than R1 by an integer multiple of the wavelength. In other words, if R2 is exactly one wavelength longer, they'll arrive in phase. If this one travels 5 wavelengths and this one travels 6, they're going to be exactly in phase when they meet there. If this one travels 5 wavelengths and this one travels 7 wavelengths, they'll be in phase. In fact, any time that R2 minus R1 is equal to an integer number of wavelengths, we are going to get constructive interference. As long as they each travel a whole number of wavelengths, whether this one went 100 and this one went 101, or whether this one went 1,000 and this one went 1,015, it doesn't really matter. What's important is that that difference is a multiple of the wavelength, and that way they will arrive exactly in phase. Now, they do not always arrive in phase. If we think about it, there should be points where they could arrive and be exactly out of phase. Keep dropping my erasers. All right, so let's look at exactly out of phase, what that would look like. Well, the picture actually wouldn't look any different. But if you got here, and instead of being a bright spot, they got there, and they actually was a dark spot. I'll put dark because there's no light there. The amplitudes have canceled out. If they are 1/2 cycle out of phase. Well, a 1/2 cycle out of phase might mean that R1 traveled 10 wavelengths and R2 traveled 10.5 wavelengths. Or R1 traveled 100 wavelengths and R2 traveled 105.5 wavelengths. So anytime this distance, so for destructive, the difference between the two has to be equal to R2 minus R1 equals M plus 1/2 times the wavelength. So instead of equaling an integer number of wavelengths, it actually equals, well, one of them, the distance is off by 1/2 a wavelength. Okay. So what's this end up looking like? Let me show you what it ends up looking like. I'm going to keep that same hot pink light source, my monochromatic light. There it is. Here's my screen. Here's slit 1. Here's slit 2. Remember, this is monochromatic, coherent light. I put a screen over here, and I let this shine on the screen. We're going to get patterns made up of light and dark, okay? I think you'll see this when you do your master in physics. I think they'll have one of the simulations where you see this. Well, directly across from this, if I go right in the middle, that's going to be a bright spot. That's going to be where R1 and R2 are the exact same length. Then there'll be another bright spot and another bright spot and another bright spot. So this is P0, P1, P2, P3, but we also get those corresponding points underneath where the path here is longer, and this would be the shorter path. There's a bright spot, -1, -2, -3. I can try and draw it. It will probably get a little bit messy. But if you think about it, this one way up here happens when these two differ by 3 wavelengths. This one right here differs, these 2 lengths differ by 2 wavelengths. This one occurs when they differ by 1 wavelength. And of course, the central one occurs when they don't differ by any. They're each traveling the exact same number of wavelengths. If we can keep right on going, and you can see how these patterns will continue. Again, if this one is longer by 1 wavelength, we get another bright spot. If we were looking at this as a screen over here, we would probably see a central bright line that was obviously bright, and then another one, maybe not quite as bright, another one. But you get what look like, we call them bright fringes, a pattern here of bright and dark across the screen, okay? Where do we get bright? Bright means constructive, and we know that constructive means the difference is a whole number of wavelengths, and destructive means that difference is m plus a half wavelengths. M can be an integer, and it can be equal to 0, plus or minus 1, plus or minus 2. dot, dot, dot. There you go. That's the end of section 20, I think it's chapter 26, 26.1. I think you should understand it pretty well. See you in the next video.